fixed point theorems. Relevance of this result was remembered in one of the first lessons, the introductory historical introduction to these codes. In reality, as we shall prove, fixed point theorems are equivalent from a logical point of view to the theorems which assert the existence of general economic equilibrium. From a logical point of view, they are the same thing, so to speak. So it is easy to understand the importance of these theorems for equilibrium theory. Well, let us begin with the definition of a fixed point. Probably you saw this topic also in the advanced course of mathematics, but however, I shall repeat all the fundamental concepts. Consider a function f, function in the traditional sense, which is defined in a certain set A and, put attention, takes values in the same set A. Is a transformation, so to speak, of A into itself, where A is a subset of the n-dimensional Euclidean space. Let us trace a graphic. This is our set A. Take any vector x in A. The function f associates to this x which belongs to A. Associates an f of x which belongs to A as well. Suppose that to this x is associated another vector like this, f of x. This is a transformation of A into itself by means of a function f. To this point, we can define the fixed point. A fixed point or unit point for this function f is a vector x star such that the image of x star by means f is x star itself. Suppose this is x star, you apply this function to x star, you re-obtain the same point of before, the same starting point. In this case, you have that f of x star is equal to x star. Is it clear? This is the definition of a fixed or unit point for a function. The traditional function, which is associated with every element of A, one and only one element of A itself. This is the definition. But the theorem tells us under what conditions at least one fixed point exists. What are these conditions? First, A is compact and convex through A is continuous. conditions, oh sorry, A is obviously no name, so it is obvious, is no name, compact and convex, and, sorry, no name, F is continuous. Under these assumptions, there exists at least one x star in A such that f of x star is exactly equal to x star. These are the assumptions which are necessary to introduce in order to have at least one fixed point, or many fixed points, of course. The proof of this theorem is due to Rauer, well-known Dutch mathematician. It's a very, very difficult proof. In reality, there are many alternative proofs of this theorem, but they are really difficult. So we shall not prove this result. Curious thing is Brouwer was the founder of a so-called intuitionism, a current of philosophy of mathematics, which avoids to employ ab absurdo demonstrations, because for Brouwer the principles of the excluded third is not generally verified. But all the proofs of a fixed point in reality are proofs of absurdo, and so from his point of view we are not very satisfied. However, since we accept the ab absurdo proof, there is no problem to us. One of the proofs starts in this way. A must be a convex compact set like this. Suppose ab absurdo that no fixed point exists according to this function f. So take any x, f of x is different from x. So f of x generates a direction from x to fx to, after a stretch, encounters the boundary of A. It is obvious. Only if f of x were equal to x, this direction would not be defined. But if for every x, f of x is different from x, you can repeat this operation for every x. For example, if you have y, here there is f of y, another direction is determined, you obtain another point of the boundary. So, substantially to every point in the set x, this application, which is derived from fx, associates an element of the boundary, and so on and so on. From this, a contradiction arises after many, many elaborations of this theorem is a generalization to an m-dimensional space of a well-known Bolzano's theorem, from the name of a well-known Deutsch German theorem, German mathematician, Bernard Bolzano. The theorem of Bolzano regards a function which is defined in set A, which is a subset of a real line. Do you remember? Suppose a function which is defined in the set, in the interval, the closed interval 0, 1, and takes values in the same interval. Oh, sorry. No, for the moment, no. The function is defined in the interval, closed interval 0, 1, is continuous, and takes some values. But you know that for a certain x, f of x is a negative number, while for x prime, for another x second, the value f of x second is a positive number. For some x, the image is a negative number, for other x it is a positive number. So the function passes by this point alpha and this point beta. Bolzano's theorem tells us that there is at least a point x star like this, such that the value of the function is exactly equal to z. A well-known theorem in elementary mathematics. But it is equivalent to assert that the function f of x minus x has a fixed point. Point such that this function has the same value of x from which we are starting. The proof of the theorem in a one-dimensional setting is elementary. But when you pass to an n-dimensional setting, many complications arise. It's not an obvious step passing from one-dimensional setting to a multi-dimensional setting. This is the reason why the theorem was so difficult to prove. However, this is the fixed point theorem by Brown. The problem with this fixed point is that it regards functions like this f. While in economics, very often we have to cope with correspondences or multivocal functions. The rule, so to speak, which associates with every x, not another element of a set, but a subset of a set A. For example, the set of all optimal production processes for a firm, the set of all optimal consumption bundles for a household, and so on. It is necessary to generalize the definition of a fixed point to correspondence and obviously to introduce some other hypothesis about this correspondence in order to prove the existence of a fixed point. So, consider a correspondence f, which is defined as before in the set A and takes values in A itself. This is the set A, take any x like this, the correspondence associated with this x, a subset of A, which is exactly f of x. Instead of associating with x only one point of A, it associates a subset of A, possibly empty. Is not excluded in the case in which this set is empty. Well, how is a fixed point for a correspondence defined in the following way? An x star which belongs to A such that x star belongs to the image of itself by means of a correspondence f. The equality between x star and f of x star, in the case of a usual function, is substituted by this condition. X star must be an element of its image. For example, this is x star. You apply to x star your correspondence, and you obtain this f of x star, and note that x star belongs to its image according to large F. This is the definition of a fixed point for a correspondence. In order to prove this theorem, some of the hypotheses which we introduced for the function remains unchanged. The first substantial, the set A must be non-empty, compact, and convex. But the continuity of F must be substituted by other properties. First property, for every x in A, f of x is a, another time, non-empty, compact, and convex set. This set f of x must be non-empty, compact, and convex as well. Like the set A. Third, most important, f must be upper hemi-continuous. Upper hemi-continuity is a typical property of continuity for correspondences. I suppose that my colleague of advanced mathematics told something about this property, and also Pacini, I suppose, introduced in order to prove upper hemi-continuity of the Demant correspondence. However, in this context, it is necessary that the function f is upper hemi-continuous. This theorem, a clear generalization of a previous theorem, was proved for the first time by a Japanese mathematician, Katutani, by simply applying the fixed point theorem by Brouwer and by a process of approximation. Also, is a difficult result. I limit myself to enunciate this alternative theory. In sum, when you have a function is a sufficient continuity. When you have a correspondence, you must suppose upper hemi-continuity. which, do you remember, means that the set, the image of f of x cannot suddenly enlarge when you change slightly the vector x. However, these are mathematical properties. Well, at this point we can proceed with our theorems. As I told you in the previous video, I shall begin from the simplest proof of existence of equilibrium. In this case, we have, as we should see, a excess demand function, so it will be sufficient to apply our theorem. But then we shall see also the case of a correspondence. In this case, we must apply Kakutani's theorem. Let us have another break.